2. We were doing the even numbered questions. This was number 2. Let's look at number 4. Just see. Okay, for number 4, we have Z is given as AX plus BY over CX plus DY. And we have to find the second partial derivative of Z with respect to X as well as with respect to Y. So we start with the partial with respect to X. So Zx is given by this. Here we must use the quotient rule. So using the quotient rule, we have the derivative of the denominator, which is A, multiplied by the numerator the way it is, then minus the derivative of the denominator multiplied by the numerator the way it is, and then we square the denominator. Okay, because we have to differentiate this again, we want to have our answer in its simplest form. So we can multiply our brackets out and collect the X terms and the Y terms so that differentiating after that will be easy. So this is ACX plus ADY minus ACX minus BCY over, let's see, yes, we treat them as constants because we're differentiating with respect to X. So only X is the variable. Let's see. Okay, please mute your mic. Okay, that's our numerator. And then in the denominator, we have CX plus DY. The whole thing is squared. So we can see that these two terms, ACX minus ACX, will cancel. And then I am left with Y times AD minus BC over CX plus DY squared. So that is my first derivative of Z with respect to X. So I want the second derivative, so I differentiate this again with respect to X. But you can see over here the numerator doesn't have an X. So I could look at this as, or I could use or I could look at this with the denominator with a power of -2 and then differentiate it like that, which might be easier, or just go ahead and use the quotient rule. Either way, your answers will be exactly the same. Okay, so if we use the quotient rule, in the numerator, we have the derivative of the denominator multiplied by the numerator. That is just 0, because the derivative of the numerator is 0. There's no X there. Then you subtract the derivative of the denominator, which is 2cx plus dy. Then you multiply by c, and then you multiply by the numerator as it is. So this is y AD minus BC over the denominator squared. So this is squared. Squared means to the power of 4. Then you would have to multiply out your brackets. Let me just see, minus 2 CYAD. Okay, that's fine. Okay, then you would simplify as far as possible. Cancel any terms that can be cancelled and see what we have left. Okay, so ZXX, so let's look at this. Okay, so we can see that CX plus DY, this one can cancel with one of these. So in the denominator, we will have a power 3. So in the numerator, we have minus 2CY times AD minus BC left. And then in the denominator, to the power of 3. So this is minus 2CY AD minus BC over CX plus dy to the power of 3. And then we have zy. So our z is that one here, except this time we differentiate it with respect to y. Again, we use the quotient rule. We have the derivative of the numerator multiplied by the denominator as it is. This is cx plus dy. Then we subtract the derivative of the denominator multiplied by the numerator the way it is. Then we square the denominator. Okay, so again, we'd multiply out the brackets, see if there are any terms that can cancel. This will give us BCX plus BDY minus ADX minus BDY. Then in the denominator, we have CX plus DY squared, and then these two can cancel. We have X times BC minus AD over CX plus dy squared. Okay, then we differentiate this again with respect to y. So the derivative of the numerator is 0. Then we subtract the derivative of the numerator, which is 2d multiplied by cx plus dy. And then we multiply by the numerator as it is. To the power of 4. Okay, so again, we can see that we have cx plus dy here. This can cancel with one of those. We'll be left with cx plus dy to the power of 3 in the denominator. And then in the numerator, we have minus 2dx times bc minus ab over cx plus dy. So this is minus 2d x, BC minus AD. This is over CX plus DY to the power of 3. Okay, which is what we were asked to work out. And number 6, if z is equal to xy over x plus y, we have to determine the value of x squared times the second partial derivative of z with respect to x squared plus 2xy partial derivative of z first with respect to y and then with x and then y squared. So basically this is just substitution. So you need to work out each of those partial derivatives and then substitute them and simplify as far as possible. So number 6, we have z is xy over x plus y, and now we find each of those derivatives and then substitute. So we start with zx. Here we must use the quotient rule. This is y times x plus y minus xy, then divided by x plus y squared. Okay, then you can see that if we multiply out the brackets, then the xy's will cancel. So I have xy plus y squared minus xy over x plus y squared. The xy's cancel. I'm left with y squared over x plus y squared. Then work out the second partial derivative. This is the derivative of that one. So the derivative of the numerator is 0. Then the derivative of the numerator is 2x plus y. And then you multiply by the numerator as it is, just y squared. Then this is all divided by x plus y to the power of 4. And again, you always want to simplify your answer as far as possible. So doing that, we can cancel. So you can see I have x plus y here and x plus y to the power of 4. So this one will cancel with one of those and I'll be left with x plus y to the power of 3 in the denominator. So this is negative 2y squared over x plus y to the power of 3. Okay, then I need the mixed partial derivative. So z xy. So I already differentiated here with respect to x. So now I differentiate it with respect to y. So I use the quotient rule, and that is the derivative of the numerator, which is 2y, and then the denominator the way it is, and then the derivative of the denominator multiplied by the numerator the way it is, and this is all divided by x plus y to the power of 4. So here, before I multiply out my brackets, I can see I have x plus y here, x plus y, and then x plus y there. So this one I'll cancel and be left with 1. This one will cancel. I won't have an x plus y, and then in the denominator I would have to the power of 3. So this is 2y x plus y minus 2y squared over x plus y to the power of 3. Then we would multiply out our brackets, and we can see that the 2y squareds will cancel. So this is 2xy plus 2y squared over x plus y to the power of 3. So like I said, the 2y squareds will cancel, and then I will be left with 2xy over x plus y to the power of 3. So my zxy, this is 2xy over to the power of 3. Okay, then we need the derivative with respect to y twice. So we start with zy. So again, z is xy over x plus y. So differentiating that with respect to y in the numerator, the derivative of the numerator times the denominator the way it is, minus the derivative of the denominator times the numerator the way that it is. This is over the denominator squared. Okay, simplify this or multiply out the brackets. We have x squared plus xy minus xy over x plus y squared. Those two cancel. I have x squared over x plus y squared. Then I differentiate again with respect to y. The derivative of the numerator is 0 minus the derivative of the denominator multiplied by the numerator the way it is, divided by the denominator squared. So this is okay, yeah, the x plus y and the x plus y, they can cancel. So I have minus 2x squared over x plus y to the power of 3. Okay, so now I have everything I need to substitute into the expression I was told to substitute in. This was x squared times zxx plus 2xy zxy plus y squared zyy. Okay, so I have this, I worked it out. I have this, worked it out. I have that, worked it out. So I just need to substitute and simplify. So this gives me x squared, then zxx, where's that? It's here, negative 2y squared over x plus y to the power of 3. It's negative 2y squared over x plus y to the power of 3, and then 2xy times 2xy over x plus y to the power of 3, then y squared times minus 2x squared over x plus y to the power of 3. So we can see all the denominators are the same. So we simplify as far as possible. So this here is minus 2x squared y squared plus 4x squared y squared plus minus 2x squared y squared. This is all over x plus y to the power of 3. And we can see that our numerator is 0. So this is just equal to 0. And number 8, we have to prove that if z is equal to sine inverse of y over x, then the mixed partial derivatives in both directions are the same. So first you differentiate with x and then with y, and then try it the other way around and show that the answers are the same. So we start with zy. So differentiating with respect to y first, in the numerator we have the derivative of our function, which is 1 over x, and then in the denominator it's 1 minus 1 over x squared. Okay, this we can simplify. So this is 1 over x. Let me just write it like this. It's 1 over x times the square root of x squared minus 1 over x squared. And this gives us 1 over the square root of x squared minus, we're getting the y. There's a y here. It's x. It's y squared over x squared. Okay, our function has a y, so I must square it exactly the way it is. So this is y squared over x squared, and the x squared here can go outside and it'll cancel with this x. So I'm left with 1 over the square root of x squared minus y squared. That is my derivative. So try and simplify as far as possible because you still need to differentiate this. So then zyx, now I differentiate this with respect to x. So this is just x squared minus y squared to the power of minus half. So the minus half will come down. Then I have x squared plus minus y squared to the power of minus half minus 1 is minus 3 over 2. And then we multiply by the derivative of the inside, which is 2x. These two cancel, and I am left with negative x over the square root x squared minus y squared to the power of 3. Okay, now we have to do it in reverse order. First you differentiate with respect to x, and then with respect to y, and then show that your answer will be exactly the same as this. So z with respect to x, this is still arc sine, so the derivative of y over x in the numerator, so this is negative y over that's negative y over x squared. That's a derivative of the numerator, and then in the denominator we have the square root 1 minus y over x squared, which is y squared over x squared. Okay, then we simplify this as far as possible. This is minus y over x squared, then the square root 1, this is x squared minus y squared over x squared. So again, the square root of x squared here, this is x, so it'll go out and cancel with one of these x's over here. So what we have is minus y over x square root of x squared minus y squared. Then that is our derivative in its simplest form, and then now we differentiate with respect to y. Okay, so using the quotient rule again, we start with the derivative of the denominator, sorry, the derivative of the numerator, which is minus 1.
Yes, I'm lost. Miss,
why are you lost?
The x. How did you factor the x out to get x and then the square root while it was x squared?
You mean this x?
Mm-hmm.
That is basic algebra. This is the same as the square root of x squared minus y squared over the square root of x squared.
Okay.
Yeah.
I get it.
Okay, and then we multiply by the denominator as it is, minus y squared. And then, yeah.
Was it not x squared and x squared? Are they not cancelling?
How will they cancel if one of them is under a square root?
Oh yeah, I got it now.
Okay, so we have, okay, that's...
Miss, for me, I didn't get that one, Miss.
Which one? Guys, this is algebra. There's no way you can tell me you don't know how to simplify this. Like I said, this is x squared multiplied by the square root of x squared minus y squared over x squared, which is x squared multiplied by the square root of x squared minus y squared over the square root of x squared, which is x squared multiplied by the square root of x squared minus y squared over x. This one cancels with that one. You're left with x times the square root of x squared minus y squared. This is from InSTEM. Okay, so that should not be what your problem is. But anyway, that is how you do it. Okay, and then where are we? The derivative of the numerator multiplied by the denominator as it is, and then we subtract the derivative of the denominator. No, I'm not saying zxx is the same as zxy. I don't think I ever said that. Okay, so here, minus the derivative of the denominator. So remember here we're differentiating with respect to y. So this is a constant. I don't need to use the product rule over here. So the derivative of this is just x. And then we look at this square root. Its derivative is it's half x squared minus y squared to the power of minus a half. And then we multiply by the derivative of the inside, which is minus 2y. And then we have to multiply by the numerator the way that it is. Okay, and then in the denominator we square. So you'll get x times x squared minus y squared, x squared. Okay, now simplifying as far as possible. Okay, right, so here when we do that, we get x negative x square root of x squared minus y squared. And here I have three negatives, negative, negative, and negative. That will leave me with just one negative. And then this 2.5 will cancel. So the half and the 2 there will cancel. And then I have x y squared. So I have x y squared. And then x squared minus y squared to the power of minus a half. And this is all divided by x squared minus y squared. Okay, then we have to simplify it. So keep in mind where we are going. This is what the answer must be. So we want only x left in the numerator. Okay, so in doing that, what we can do is split these fractions up. Maybe that will help us. So the first fraction will be minus x square root of x squared minus y squared over x squared minus y squared. And then the second one will be minus x squared minus y squared to the power of minus a half over x squared minus y squared. Okay, so this x will cancel with one of those, and then here this one will cancel with that, and then we're left with square root of x in the denominator. So this first fraction is minus 1 over x square root of x squared minus y squared. And then same thing here, x there, and 1x will be left. And over here in the denominator, what we have left is now this, the square root of x squared minus y squared to the power of 3. Okay, then we can try and combine the two fractions together. Right, I see what I did here. Okay, this one here, this is to the power of 1. This is to the power of a half. Why did I write that? Let me just see what we did here. Okay, so we have minus x square root of x squared minus y squared. That's fine. X squared, x y squared. Okay, that's fine. Then we have minus x, the square root of x squared minus y squared. Okay, then minus 1x. Okay, that's fine. Okay, that's fine. Okay, right. So what we can do now is just combine these two fractions together. And before we combine them, the denominators must be the same. So this one here, I need to add an x because there's an x over there. And this square root of x to the power, square root of x squared minus y squared, it has to become the square root of x squared minus y squared. So I need to multiply by x squared minus y squared. Okay, so this is minus 1 x squared minus y squared. This is x square root of x squared minus y squared to the power of 3. And then, yeah.
Miss?
Yeah.
I have a question. In the second fraction, isn't it there's supposed to be x also, like x square root of x squared minus y squared, everything to the power of 3?
Yes. Yes. So it's this x here. Yeah. Then the denominators will be the same. So this is minus y squared over x square root of x squared minus y squared to the power of 3. And the denominators are now the same. So we can just combine the numerators. So this is minus x squared plus y squared minus y squared over x square root of x squared minus y squared to the power of 3. So you can see that these two will cancel. After minus x squared, not write it. So here I have x squared, and over there I have x. So this x will go, and I'll be left with an x in the numerator. So this is over the square root of x squared minus y squared to the power of 3, which is exactly what I had over there. Okay, so this, I guess, illustrates the importance of choosing the right order of differentiation. So when I differentiated, where's the question? When I differentiated with respect to y and then with x, you can see I can do it in just 3 steps, not very complicated to find the mixed derivative. But when I do it in the other way, first I differentiate with x and then with y, it is quite long, even though the answers are the same. So try and pick, whenever you're asked to find the mixed derivative, pick the way that is going to be easy, because the answers are the same. And you can see that when there's a lot of calculations, it's very easy to make a mistake. But anyway, you will know which one is the easiest. Yeah.
So like the second last step, right? Miss only differentiated one part. So there's no problem if, if I want to make the same, I just differentiate the part that I think it's missing. Then the other one, I just leave it like that.
The second last part, this one here?
Yes, miss.
Here I didn't do any differentiation. The differentiation was done here. After that, it's simplifying.
All right, miss.
Okay. Great. Then the next thing we look at is total derivatives, or as it said in your book, the change of variables. So these are the total derivatives. Okay, So when we talk about multivariable functions, like z is a function of x and y, so we have z. This is a function of x and y. And sometimes, and as is usually the case, you will find that x is a function of some other parameters. So x is also a function of maybe u and v. And then y is also a function of u and v. So z depends on x and y depends on u and v, and x also depends on u and v. And now the question may be, can we find the derivative of z with respect to u and the derivative of z with respect to v? So that will be the partial derivative. So the partial derivative of z with respect to u. So see that z is only in terms of x and y, but x and y are in terms of u and v. Now we want to find the derivative of z with respect to u. Here we just use the formula, the partial derivative of z with respect to x multiplied by the partial derivative of x with respect to u. So you can see it looks like these two cancel, then you're left with dz du, and then you add the partial derivative of z with respect to v times the partial derivative of, not v, sorry, of y with the partial derivative of y with respect to u. So again, it looks like these two cancel and you're left with some du and du over there. So this is how we work out the total derivative if z depends on x and y, and then x and y also depend on some other parameters. And similarly, the partial derivative of z with respect to v, this is the partial derivative of z with respect to x times the partial derivative of x with respect to v, partial derivative of z with respect to y times the partial derivative of y with respect to really, there isn't anything particularly difficult because we know how to find the partial derivative of z with respect to x, how to work out this one, how to work out all of them. Then the rest is just substitution and simplifying. Let's look at some examples of finding this total derivative. So let's say z is the square root of x squared plus y squared, and we're also told that x is equal to e to the power of r cos theta and y is equal to e to the power of r sine theta. Now we want to find what is the derivative of the partial derivative of z with respect to r, as well as the partial derivative of z with respect to theta. So we just use the formula as it is given. We start with the partial derivative of z with respect to r. This is, no, I can use the shorthand. This is z with respect to x times x with respect to r plus z with respect to y times y with respect to r. Okay, so if we differentiate z with respect to x, we have a half x squared plus y squared to the power of minus a half times 2x. And then we differentiate x with respect to r, which is e to the power of r cos theta. So that's this first part over here. And then this one, we do it in the same way. The derivative of z with respect to y, this is a half x squared plus y squared to the power of minus a half, and multiply by the derivative of the inside, which is 2y, and then multiply the derivative of y with respect to r, which is e to the power of r sine of theta. Then from here we want to simplify as far as possible. You can see that the half and the 2's will cancel, and then what we are left with for the first term, we have x e to the power of r cos theta over the square root of this. We have x e to the power of r cos theta over the square root of x squared plus y squared. And then for the second one, we're left with y e to the power of r sine theta over the square root of that. So this is y e to the power of r sine theta over the square root of x squared plus y squared. So we can see here the square root of x squared plus y squared is a common denominator. So we can rewrite this as a single fraction and even factor out the e to the power of r if we like. So this e to the power of r x cos theta plus y sine theta over the square root of x squared plus y squared. So that is what we have. Okay, so again, just applying the formula, nothing particularly complicated there. Then we can also find the partial derivative of z with respect to theta. Again, this is z with respect to x, x with respect to theta, plus z with respect to y times y with respect to theta. Then z with respect to x, we already worked it out there. It doesn't change. So I can just write the one after I've cancelled everything. So this is x squared plus y squared to the power of minus a half. And then x with respect to theta. Remember, x is e to the power of r cos theta. So the derivative of cos theta is minus sine theta. So I have minus e to the power of r sine theta. Okay, so that's z with respect to x, and then x with respect to theta. Then z with respect to y, I already worked it out, it's over here. So this is y x squared plus y squared to the power of minus a half. And then now I differentiate y with respect to theta. So remember, y is e to the power of r sine theta. The derivative of sine theta is cos theta. So here I multiply by e to the power of r cos theta. And then we do the same thing, simplify it as far as possible. And that leaves us with for the first one, in the numerator we have...
Quick go big man.
Okay, for the first one, in the numerator we have x negative e to the power of r sine theta. This will be over the square root of this. So this is minus x e to the power of r cos theta. That's the first fraction. So I can already see that the denominators will be the same, so I'll just put one big fraction. And for the second one, I have e to the power of r y cos theta in the numerator. So this is y e to the power of r. For the first one, it was sine theta, not cos. And then this one is cos theta. And then the square root of x squared plus y squared. Okay, then another example, we have z is equal to 2x plus 3y, and we are told that x is equal to sine of u minus v, and y is ln of u plus v. Then we have to find the total derivatives. We start with z with respect to u. So first differentiate with respect to x, then x with respect to u, z with respect to y, and then y with respect to u. So these are pretty simple fractions to differentiate, nothing too complicated. When we differentiate this with respect to x, our answer is 2. Then x with respect to u, this is just cos of u minus v. Then z with respect to y, this is 3. And then y with respect to u, this is 1 over u plus v. Okay, so that is the total derivative of z with respect to u. Then the same thing with z with respect to v. Then we just substitute. We already worked out z with respect to x and z with respect to y. So we can just write them. Z with respect to x is 2. And then x with respect to v is minus cos u minus v. And then z with respect to y, we got 3. And then the derivative of y with respect to v is just 3u plus v. So if I were to write this nicely, this is 2 cos u minus v plus 3 over u plus v. Then we can do one question from exercise 2.5. Let's do the odd numbered questions this time. Okay, for number 1, we have z is equal to e to the power of xy, and then we are told that x is ln of uv and y is cos of uv. So now we want to find the total derivative of z with respect to u as well as with respect to v. So z with u, we say this is z with x, x with u, z with y, then y with u. So z with x, we know how to differentiate that. This is y, e to the power of xy, and then z with, sorry, not z, x with u, this is v over u. Then z with respect to y, this is x e to the power of xy, and then y with respect to u, this is minus v cos, it's not cos, sine of uv. Okay, and then you close the brackets there. Okay, simplify it as far as possible. Sorry, this is uv. Then, okay, now it's fine. There should be a v here. The derivative of this with respect to u. Yeah. Okay, so the v's can cancel. So I have y over u e to the power of xy, and not a plus, that should be a minus. And again here, there should be a v multiplying here. So times v there. So it's minus sine of uv times v. Okay, and now we multiply out, simplify as far as possible. This is vx e to the power of xy sine of uv. Okay, let me just see, y over u e to the power of xy minus vx e to the power of xy sine of uv. Okay, so that one is fine, and the second one you can try and do that on your own. And let's see, yeah, I think we'll be done soon. Okay, so we'll stop here for today and continue tomorrow at 11:30.